Yes, so hello everyone, great to be here. So as said, my name's Chelsea. Today I'm going to be presenting a formalisation of the Balog Szemerédi Gowers Theorem, which is a result in additive combinatorics, which we completed in Isabelle HOL. So this was joint work alongside two of my co-authors. We all contributed fairly evenly. Unfortunately, Angeliki and Mantas can't be here today. I will say they're the mathematicians of the group. I'm the computer scientist, so we'll see how this goes. But they are also very happy to be any questions we pass along to them as well after the presentation. So this is a formalisation talk, but I'm not going to try to fully explain all the mathematics involved because it wouldn't be possible in 22 minutes. So what I'm going to try to do is give you a bit of a taste for some of the mathematics that we're using here, and then focus on some of the challenges and interesting parts of the formalisation itself. So as said, this is a theorem in additive combinatorics. Which, although it has combinatorics in the name, it's kind of actually this really interesting mix and intersection of a number of different fields of mathematics, which it both uses and then feeds back into, and even has some interesting applications in computer science, which I find quite interesting from a verification perspective. But simply, it's looking at the additive structure of sets. So when I say additive structure, what do I mean? So looking at things like sumsets and different sets being two of the crucial ones. Which we'll be using both of in today's formalisation. And then you can also define properties such as additive energy, which we've given up here on the screen. So really quite simple concepts that raise a lot of really interesting questions. So the Balog-Szemerédi-Gowers theorem itself started as this result by Balog and Szemerédi, which says, given a finite subset with a set additive energy in an abelian group, it must contain a subset itself such that that subset's cardinality is really large, but the cardinality of its sumset is quite small. And Gowers then added on to this by providing much better bounds in his proof, which also used some really kind of different proof techniques which have become quite valuable in their own right in the field. And the result itself was really important to the proof of the celebrated Szemerédi theorem. So why formalise? I'm hoping I don't need to tell this audience why we want to formalise mathematics generally. Combinatorics is definitely growing significantly in formal libraries. We've seen a lot of progress in Isabelle recently, as well as other proof assistants such as Lean. It's a really intuitive area of math, so it makes it quite interesting often to formalise. But specific to this, it really comes down modern, interesting, relevant. Additive combinatorics is a really active field of research. It's got many open problems. The Balog-Szemerédi-Gowers theorem hasn't been formalised before and is quite a relevant tool in current research. And specifically, its proof techniques also involve this really interesting interplay between additive combinatorics, a bit of algebra, graph theory, and probability theory, which raises some really interesting kind of questions when you go to formalise it. So our key contributions, we worked through a number of background bits as required, which we've detailed in our paper. What's particularly interesting of the background is we actually developed a new graph theory library for this. So I'm going to touch on briefly why we went about doing that. And then of course, the main result being the formalisation of the theorem, which one thing we looked at specifically is using this locale-centric approach, which is an approach that uses Isabelle's module system, which we call locales, quite extensively, quite successfully as well, I think. And then we also formalised a number of additional related results and some alternate versions, which I won't go into today, but again, are in the paper. So background resource-wise, there wasn't a lot in sumset kind of theory in Isabelle at all, so except for some previous work by Angeliki, one of my co-authors. So we built a little bit on that. Notably, we also built on this AFP entry by Balog in the formalisation of algebra rather than the built-in distribution version of algebra in Isabelle. This is because this new version uses this locale-centric approach, which is much nicer to work with in a really natural way mathematically. So, graph theory. We are going to take a detour into graph theory in this proof in additive combinatorics. And what we kind of found is, yes, there are many formalisations of graph theory in Isabelle. Some are given up there on the screen that you can see. The problem is that there's not really that many general ones specifically for undirected graph theory. So a lot of the formalizations that exist are very specific to certain needs, algorithms, mathematical problems. The one general library is this digraphs library, which works quite well. It does use a mixture of records and locales, but as you can see, that structure is quite complex when you're only reasoning on undirected graphs, something that the author acknowledges in the work as well. The previous version of undirected graphs we had been using is this really simple one, which effectively just models the edges as sets, and a graph as some combination of a vertex and an edge set. The issue with this is that, as you can see, it turns out it uses this type synonym where it sets vertices to natural numbers. Now, if you want to do any kind of modeling with graphs, their vertices are anything but natural numbers, such as elements of an additive abelian group, this becomes very inflexible and frustrating to work with. And so this is quite interesting. We've used this library quite extensively for things like Szemerédi's regularity lemma, but really just wasn't suitable in this case. So rather than going and developing another really proof-specific version of graph theory, I went away and developed this general version of an undirected graph theory library using locales. Locale, for those who haven't seen one before in Isabelle, you've got parameters and you've got assumptions, fairly simple structure. You've got direct inheritance, such as a simple graph simply adds this assumption that each edge is of size 2. And you've also got indirect inheritance. So a bipartite graph, its assumptions here imply that assumption that therefore the edge must be of size 2. So rather than add an unnecessary assumption into the locale definition by inheriting directly, we can establish inheritance after the fact. Locales have proved like really powerful to work with. I went away and worked on this separately for 2 or 3 weeks, and my co-author Mantas, who was an intern with us, a mathematician who had no prior experience in Isabelle, was able to start integrating those really easily into the main formalisation. The other benefit of this is that it does allow us to do some flexibility. So if we want to go and use a different representation of graphs that's also defined using locales, you can do that quite easily. And you can see examples of that in the AFP entry if you're interested. A few just notes from a perspective of this formalisation. We did need a concept of graph of loops. Now, working with graphs as where edges are defined as sets is really handy in Isabelle, just automation and previous results. So how we went about doing this is making a loop edge a singleton set. And that worked quite effectively in the end. And we also defined the parameters for a bipartite graph as 2 separate sets. That, again, was much more natural to work with than in the context of the locale. So getting back to the theorem on hand, this is now the formal statement of that theorem that I gave you earlier. You can see really the only thing that we've kind of done differently is we've now specified the additive energy and the exact bounds for what we mean by small and big of that different set. We're also using the different set version here of the proof. It's an analogous version for the sumset. And this is just how the paper that we were basing our work on started. So it's how we started the formalisation as well. So our proof, our formalisation, really followed the proof that was on paper as well in terms of its overall structure. And this is kind of what it looked like. We take this detour, starting off by going into graph theory. So lemma 3.1 and 3.2 are both stated completely in terms of graph theory. You wouldn't know they had anything to do with additive combinatorics. Lemma 3.1 actually then went and used some really interesting probability-related techniques. And lemma 3.2, while its proof was quite graph theoretic, drew on these 2 technical probability lemmas. Lemma 3.6 was stated completely in terms of kind of algebra additive combinatorics, but its proof was almost entirely graph theoretic. And then this main theorem was just a corollary of lemma 3.6. So it's this kind of interesting detour through a few different kind of areas of math that we touched on. So I'm going to focus on this main central line of the proof today, but we do have details of all aspects of the formalisation in the paper. So let's start with lemma 3.1. So the interesting part about lemma 3.1 is that it uses something called a dependent random selection method, which is a probabilistic method in combinatorics. And effectively what this lemma is trying to do is find a subset x dash within the main set x so that we have many paths of length 2 between all elements. And what we kind of are asking is how do we find that random subset so that it has some better properties than we had before, but use the structure of the original set still. And this is where this method comes in. So this is basically what the method looks like on paper at the top, and this is what it looks like in Isabelle underneath. So what we're doing is instead of defining this x dash completely randomly itself, we define it by picking some other element randomly, hence the dependency, and then letting x dash, in this case, be the neighborhood of y. Right? So the one different and interesting thing that I'll note here in Isabelle that we have to do is set up a probability space You obviously don't need to do that at all in paper. They very, very rarely will tell you anything, in fact, about the probability space that you're suddenly doing things on expectation, etc. about. So this setup here is something that we've done and provided many examples of for combinatorics and graph theory throughout this paper. P probability space is actually a locale itself. So we've established an instance of that locale. And then you can see it's quite easy to reason, well, the expectation of neighborhood y, so x dash, in the context of the probability space P is equal to this value here. And the reasoning follows actually fairly easily in Isabelle once you have that set up in place. So moving on, lemma 3.2, intuitively what this is doing is finding many paths of length 3 between vertices and different subsets. So this is the formal and the informal statement of this theorem. Again, the nice thing about Isabelle is it's quite easy to read the mathematical context. A few interesting points just about the statement itself. You'll see in the original statement we're referencing the number of paths. We are here using the definition of walks. This comes in quite common. It's quite common in combinatorics that definitions are quite ambiguous depending on the literature. And one of the things that we found halfway through the formalisation is that we were actually supposed to be using walks. So the other interesting thing about this is the lemma statement itself, which specifies that it's in the context of this bipartite graph locale, for those who are unfamiliar with Isabelle syntax again. So this means that we can use the variables x and y without redefining them. We know all of those. We know the assumptions about them based on that finite bipartite graph locale. So the really interesting part of this proof from a formal perspective was that we had to use many different auxiliary structures from both probability theory and graph theory. And this was a great kind of example of how you can use locales and lots of instances of locales and transport information, as we're calling it, across the proofs and across the different structures. So you can see we had 3 different kind of probability spaces on different elements. We also had several different graph constructs. For example, we had to create a new bipartite graph instance, which we called H. Also a graph of loops was required. So each of these interpretations, of course, requires a proof that it does, in fact, fulfill the assumptions, etc., of the locale. And then once you have all these set up, it's really easy in Isabelle using this to kind of see, draw on lemmas from these other instances of the structure as well as the local instances. So the blue, underlined blue things here are basically the local kind of theorems and definitions. And then you can see the ones that we're pulling in from these new instances that we've created as well. So we did this as a very simple example, but we did many different cases of using these kind of multiple instances of different locales and sometimes even the same locale at once. So that now brings us to the graph-theoretic Balog-Szemerédi Gowers theorem, as a lot of literature will call it, or lemma 3.6. And you can see at this point we're getting quite close to that main statement of the theorem. We've got 2 sets, both which are big, and a different set that's quite small. So we're getting very close to it. And how the proof of this actually works is we go away and create an auxiliary graph construct. We can apply that previous lemma to get 2 really kind of big sets based on paths of length 3, which have these paths of length 3 connecting them. And then using those facts about paths of length 3, we can kind of use something called the theta popular difference, which I'm going to define in a minute, to do a whole lot of counting, which I'm going to gloss over, and create some bounds. So what does the graph construct look like? Because this is the interesting part. Effectively, what we do is we say, well, each partition of the bipartite graph is a copy of that subset A in our abelian group. And then we only connect the 2 edges if the difference between those 2 elements is theta popular, right? Then we can apply lemma 3.2. So this graph, again, quite easy to define in Isabelle. The one kind of interesting thing we had to do is obviously differentiate between the 2 copies of A, so add some kind of tags. So we satisfied this kind of disjointness properties. And then the edge set we just defined slightly separately, so it made it easier to state and reason on. So this proof was probably, I think, the longest in our formalisation. It was about half a page on paper, so definitely not the longest proof on paper of the 3. And what it really came down to was, I guess, 2 main elements of the formalisation, which are quite actually typical, I think, in terms of current challenges that we're seeing. So this first line here is just looking at the cardinality of a predefined set, 1 throwaway line on paper, 113 lines in Isabelle. Obviously, this is using ISA, which is quite an expressive proof language, but it's still a lot of lines and kind of work that's not described otherwise. The other thing we had to do quite a bit of was these kind of weird kind of projections between different objects that, again, on paper they wouldn't really worry about because it's very obvious. So one example here being a sextuple and one being a tuple of 3 pairs, right? From those paths of length 3 into just a sextuple itself. So for each of these functions that we define, you have to prove properties around bijectivity, etc., all of that kind of stuff, which just wouldn't be done on paper because it's quite trivial to look at it and see it's true. So that now brings us to the main theorem, which is actually, again, just that corollary of what we had before. We take A dash to equal C from the previous lemma, apply the root of triangle inequality, well, it's another theorem, and get the bounds that we want. So the reason I'm showing this is so that you can see how that compares to the formalisation. So what you can see is the first 3 dot points translate pretty simply, 1 or 2 lines each, which is really nice. You can see where the lemmas are applied. That last dot point takes a little longer, mostly because it's all that kind of arithmetic kind of rearranging of stuff, which just takes longer formally and wouldn't be done on paper. So overall, this translated pretty nicely to finish off with. So a few kind of the main pull-out challenges and highlights. Definitely using locales has continued to be really useful. We found that definitely kind of the easiest way to work with construct different structures, different hierarchies of structures as well, and for newcomers as it turns to use as well. In our case, this was the first time we'd really experimented with using locales from a number of different areas of maths, and it was really quite effective and easy to do, and quite natural to do as well, which was nice to see. Probabilistic methods, we know of 2 previous examples in Isabelle. I'm not sure about any other proof assistants that use the probabilistic method. The main challenges we found was finding theorems. A lot of it's a measure theory. A search thing's not going to be able to bring up something on expectation when it's looking at the integral version of it, and also setting up that formal probability space that wouldn't be done on paper. So we've aimed to provide many examples of doing that throughout this work. Notably, things that contributed to that De Bruijn index factor is the cardinality and counting lemmas, as well as that stuff that just wouldn't be done on paper. And to finish, so this was 3 of us working quite jointly on it. It took under 2 months. That included someone who had no prior experience of Isabelle, as I said, was an intern with us, and that new graph theory library. So it was pretty speedy to do for a fairly useful and advanced piece of mathematics. This is the first formalisation, but we hope that the proof techniques itself are equally useful. We've, as I said, formalised a number of supplementary results and alternates, which are available and detailed in the paper, and want to continue doing more additive combinatorics and probabilistic methods in combinatorics moving forward. So those are my co-authors' contacts, and those are the Isabelle AFP entries. Happy to take questions.
Questions, please.
Hi, that was really nice and good job. You stated the theorem in terms of sumsets and additive abelian groups.
Yes.
How hard is it from your statement to get a version for multiplicative abelian groups and product sets?
I wouldn't imagine it would be too hard. I said we did prove a number of analogous kind of versions between the sumset and the different set version. So I think it would just be about looking at the locale and how we've defined and the additive abelian group context compared to changing that structure slightly. But I imagine it would be very similar kind of techniques. I don't have the mathematical background, so probably.
Sure, so it would be adjusting locales rather than redoing the entire proof.
I think you'd have to adjust the locale, but you might be able to do some, if you generalized it, I think it would be quite easy to share some stuff between the proofs, from what I understand.
Okay, makes sense.
Yeah.
Thanks.
Thanks for the clear talk. I just have a question about whether you've run into any situations where you wished you had a better interaction between like type classes and locales, or whether that did not come up in your work.
We found that using locales, we haven't really had any issues with kind of type classes or kind of typing concerns. It's actually been able to get us around a lot of those a lot of the time, which is quite useful. The one thing I personally find can sometimes just be something you have to work around and get familiar to use it well is locale definitions. You kind of need to say this is a locale instance, and you can't say, oh, this function is taking a type of a graph, because a graph is a locale structure. So you more have to say a slightly different version of that. That's probably the only thing that can be frustrating. Cool, no worries. Thank you.